we can use this radioactivity in general in constructive processes, particularly the production of power. And those of you who would work in the space program or join NASA, by the way, we have several students, in fact, who joined NASA after taking our class. Then we'd like to look at how radioisotopes are used for space exploration. So that would be the topic for today. One particular isotope will come into our emphasis. That would be the isotope of plutonium-238. We'll see what are its properties. But alternatively, we can use other isotopes like strontium-90, or we can use isotopes like thallium-204. So we will simply get going and share the screen here and see how this is being done. Following the use, the engineering and scientific uses of the radioactive isotopes, we will explore the use it in other applications, and we look further into fission systems. So we go to our web page here. Notice that the calendar has been adjusted according to what people have asked. Friday, July 1st would be our first midterm. Halfway through the semester, we'd have our second midterm, July 18th. And the final is set on August 1st. You will be instructed how to proceed. It will be a take-home exam, obviously, since we are doing it on the internet. All right, so when we deal with radioactive processes, we will be interested in food preservation by radiation later on, but we are going to switch to the application in space nuclear power applications. And the chapter is going to be the radioisotopes power production. As I suggested, I'm putting here a background, in fact, of the northern lights. A very nice picture. It's an interaction between space radiation, in that case, and the Earth's atmosphere. In the use of radioactive isotopes, the technology has started earlier in 1956. And we'll see why we need to use radioactive isotopes, even if we are very close to the atmosphere of the sun. One could suggest that we use photovoltaics, but the strong solar radiation and the strong magnetic field of the sun would not allow us to do that. So radioisotopes come and become important in that case. In 1956, the first application was designated as systems for nuclear auxiliary power. So that's an acronym in the form of SNAP. And for example, the SNAP-3 device was launched in 1959. It was the size of a grapefruit. It was only 4 pounds and generated a small level of power.
Professor, you're not sharing your screen.
Oh my gosh. Okay, let me see what is going on here. Thank you. Share screen again. Now it should be sharing now.
Yeah, now I can see that.
Thank you. Yeah. That's the need for the co-host. Okay, I'll restart again. We are looking at the use of radioactive substances, radioactive isotopes in space applications. They found its use starting 1956 in what has an acronym as Systems for Nuclear Auxiliary Power, SNAP. The SNAP-3 device used the isotope polonium-210, which is an alpha emitter. Remember, in the decay chain, of uranium-238, we discovered that polonium-210 is generated, but in fact, that polonium-210 would be produced in particle accelerators. You'll use hydrogen beam in the accelerator and irradiate bismuth-212, and then you end up with polonium-210. It's a very powerful alpha emitter, so it produces alpha radiation, it produces heat, but we'll see later that heat generation can be turned into electricity by different processes like thermoelectricity. It has a small power, 2.5 watts, much more, of course, than the Chicago Pi #1 that produced only half a watt, and much less than what we'll see later in power reactors that produce 3,000 gigawatt or 3 gigawatts or 3,000 megawatts or 3,000 million watts of electricity. It provided a total of energy of 11.6 kilowatt hours when the heat energy from the alpha emitter was converted into electrical power, and it operated over a 280 days period. You'll find that those radioactive isotopes are designated as RTGs for radioisotope thermoelectric generators, and it's used by NASA in many missions, including the Apollo missions to the moon. In fact, one of those generators was left on the surface of the moon detecting seismic activities. The Viking missions to Mars, Pioneer, Voyager, Ulysses, Galileo, Cassini, and the Pluto New Horizons, that one went out beyond the outer reaches of the solar systems. So the designation is RTG, and I invite you to visit the site, NASA site, and in that case, you can learn more about beyond what we are going to cover today. Pioneer 10 is a spacecraft that used such devices, and as I said, it is beyond the solar system right now. What are the applications that radioactive isotopes are used for space applications? They're used in 5 different instances. When the satellite orbit passes through radiation belts, we'll see that the Earth has, in fact, you could see it in the aurora borealis, that radiation from the sun is trapped around the Earth in what's called the radiation belts. Those radiation belts have very high levels of radiation, so any instruments would be damaged. So in that case, if you try to put photovoltaics close to the radiation belts, they're named the Van Allen belts, named after the persons who discovered it, and the solar cells would be destroyed. So radioactive isotopes would save the day in that case. Operations on the moon or Mars, where we have long periods of darkness. So on the other side of the moon, it's dark. You know that the moon is inertially coupled to the Earth. So we always see only one face of the moon. Just look at the moon at night. It doesn't rotate. It follows its face follows the orbit of the Earth. The other face is dark. So there is no solar radiation there, after all, to use photovoltaics. Also, this period of darkness, like on Mars, are associated with very low temperatures. The night on Mars is below 0. So any batteries or electronic instrumentation would freeze. So in that case, you need a radioactive isotope to provide heat to keep the instrumentation warm in the cold of space. Otherwise, we cannot operate our electronics. Just witness your car battery in the winter. If it freezes, you cannot start your car. Space missions in opaque atmospheres, such as Venus. Venus is surrounded by clouds of carbon dioxide. Solar cells would be useless. There is no light there beyond under the clouds. At distances far from the sun, the solar flux there is very low. So if you start trying to use fuel cells or batteries or solar arrays, that would have to be huge in size, the size of a football field maybe, and deploying it can be affected by mechanical failures, and radioactive isotopes in that case are compact, and they fill the need in that case. And of course, as I suggested, heating the electronics and storage battery in the deep cold of space. A trivial piece of information here is that space is very, very cold. It's minus 245 degrees Fahrenheit. So in that case, you need the power generation as alpha particle emissions that lose that energy and heat our instrumentation and keep our batteries from freezing in general. There are many different isotopes for power generation, and designing them is a simple matter. So let us see how you can design an isotope for power applications. First, let us show you one of those actual isotopes in use. This is a little pellet here, a metallic pellet that is 40 grams in weight, or 1.4 ounces. The size, think of it about the whole device is 1 inch by 1.3 inch. The little tiny piece here of that plutonium-238 is maybe the size of a penny, as you could see here, but it is placed in a graphite enclosure as a shield enclosure that can take very high temperatures. So when you are launching it into space, there has been situations of the launch failing, and you don't want the plutonium to fall down and spread itself on the surface of the Earth if the launch fails. So the graphite provides a protection first against gamma rays emissions from the plutonium-238, as well as taking very high temperatures. Let's say they can withstand a fire. A little tiny 1.4 ounce or 40 grams of that plutonium-238 produces for us a heat output of 1 watt of thermal energy, 1 watt or 1 joule per second. You want 10 watts? Oh, you use 10 of these. You want 100 watts? You can use 100 of these. So it goes up linearly. So how do we figure the design in that case? First, the design would have to choose the isotope to be used. We have to consider the radiation emitted by the isotope. And we start by what we defined in the previous chapter as the activity of the isotope at time t equals 0. Remember, it is equal to the decay constant. The decay constant is a natural logarithm of 2.6931 divided into the half-life of the isotope that we choose for that purpose. And sub-0 would be, from Avogadro's number, the initial number of atom. And if you have a certain number of grams from Avogadro's law, he would divide the number of grams, or the in the CGS system of units, into the molecular weight in atomic mass units. You get the number of moles, or the number of gram molecular weights multiplied into Avogadro's number. From this knowledge, I can turn that n sub-0 here, the initial number of radioactive atoms or nuclei, to be more exact, into a mass. So let's modify that equation by using Avogadro's number. These are the internals, by the way, of one of those devices. The plutonium-238 would be in the center here, several layers of shielding, a graphite plug. And if you leave that plutonium-238 sitting on a table, it would look like this, like maybe an inch in diameter. The interesting thing is that it would glow red hot from the emission of the alpha particles that lose that energy then and heat up the isotope. So this is a small disk now, that's not a sphere, a disk. It glows red hot from its own internal heat generation. Notice that plutonium-238 is an isotope that cannot be used to make weapons because of its internal heat generation. You could see it with your own eyes here. And in that case, it would destroy any surrounding explosive. So you cannot use an implosion device. The use of plutonium for weapons is left to plutonium-239. So in the case of the equation that we wrote for the activity earlier, we are interested in the activity per gram of the material. So if we take the activity lambda n sub 0 divide into G, the weight of grams of the isotope, you get the specific activity. Now, if you take that specific activity, this is becquerel per gram. Becquerel is 1 disintegration or 1 decay per second. If you multiply this by the energy release in each decay, you find that now you get, instead of becquerel, you turn it into million electron volt per gram per second. So in that case, the activity here, becquerel, is disintegration per second. This turned now into energy release in million electron volts per second. Oh, what is million electron volts per second? This is energy release per unit time. That's what we designate as power. So that initial specific activity, A sub 0 prime, becomes really the specific power, P prime, the power generated in million electron volt per second per gram. As I suggested, we can use Avogadro's number and turn my n sub 0 here, the number of atoms of the isotope that we are using, into a mass, G, if you use Avogadro's law. The initial form of Avogadro's law is G over M, the number of moles or the gram molecular weight, M being the molecular weight or the atomic weight of the isotope. And Avogadro is that constant of nature that we call Avogadro's number, 0.6 10 to the 24 nuclei per mole. All right, so let's substitute, instead of n sub 0 here, G, Avogadro's number divided into M. And our equation for the power generation per unit weight of the isotope is E, the energy released by the radiation that is characteristic of the isotope, multiplied into the decay constant, multiplied into Avogadro's number, divided into the molecular weight. So this is the power per unit mass. Let us convert our million electron volts into watts. And the 1 million electron volt per second is 1.6 10 to the minus 13 joules. So if you take it per second, it becomes joules per second. So 1 million electron volt per second can be turned into watts. We like to describe power in general in engineering and science in terms of the unit of watts. So that let's convert that specific power into watts per gram. So that would be specific power, meaning power per unit mass. So that adds here a constant in front of our equation. And here we are ready to design an isotope that generates a certain number of watts per gram of the isotope. Now, if you are writing that equation here, these watts are not any form of energy, it's primarily thermal energy. But we'll see in a moment how we are going to convert that thermal energy or heat into electricity. And in that case, we have different processes for the conversion of heat to electricity. So if you want to talk about not the thermal watts, notice here I added TH for thermal. If you want to turn it into electrical watts, you have to add to it the efficiency of the process, the thermal, overall thermal efficiency of the process. So the design equation for obtaining a given amount of power per unit mass or specific power of any isotope that is radioactive is simply that equation right here, 1.6 n up to the minus 13. The thermal efficiency of the process producing the electrical power, E, the energy released by the disintegration, the main form of disintegration of the isotope, multiplied into the decay constant, multiplied into Avogadro's number, divided into the molecular weight of the isotope. We'll use that equation later on to design a thermoelectric generator of our choice. I did mention that the choice so far in the space program is plutonium-238, an isotope of plutonium that generates lots of heat because it's an alpha emitter. The alpha particles are emitted, and they can get a disk or a sphere of plutonium or a cylinder of plutonium-239 to really glow red hot. So how do we produce it? We produce it by using neptunium-237. Remember, neptunium-237 was the top of the artificial human created decay chain, other than the other decay chains like for uranium-235, uranium-238, and for thorium-232. It is produced in reactions with fast neutrons in existing nuclear reactors. So a neutron gets absorbed in uranium-238, and it's called an end-to-end reaction, meaning that that neutron is multiplied. That reaction produces 2 neutrons and turns our uranium-238 isotope into uranium-237. Uranium-237 is unstable. It has an excess number of neutrons, as you could see, because we added a neutron to its nucleus here. So it decays by emitting a negative electron, an anti-neutrino, I'm ignoring it, a gamma photon, I'm ignoring it here. But primarily, we get the isotope of neptunium, neptunium-237. So from reactor fuel, we can separate that neptunium-237 when we reprocess the fuel, when it's chemically treated. If you put it back in a nuclear, in that case, a research reactor, and absorb again a neutron into neptunium-237, it turns into neptunium-238, and a gamma photon is emitted. And here we added a neutron to the nucleus of neptunium-237. It's unstable, so it starts emitting a negative electron and turns into plutonium-238. And then that 238 now is what is used in those space probes. We have, because it has a longer half-life. This happens really almost instantaneously, but this here has a half-life of 87.74 years. So we can design probes that could use the radioactivity from that plutonium-239 within the range of several 20 years, 30, 40, 50 years before its power decreases to 1/2 the original power. So let us take the isotope 238 and substitute into the equation of our specific power and see how much power we can produce per gram of a given isotope in the equation that we derived a few minutes earlier. If you go, the constant comes here. If you go to the chart of the nuclides, you'll find that plutonium-238 emits an alpha particle, and that alpha particle has an energy per decay or per emission of an alpha particle of 5.54 million electron volts. So in that case, that E here is 5.544 million electron volt. Lambda is a decay constant. So the decay constant is 0.6931 divided into the half-life of the isotope. We said that the half-life from the chart of the nuclides is 87.74 years. So that's 87.74 here. But remember, the unit that we use is the becquerel. So this is disintegrations per second. So we have to be careful. This is years half-life. So we have to transform this into 365 days, 24 hours per day, 60 minutes per hour, and 60 seconds per minute. So we have to be very careful with the units in any of our calculations right here. Then we are left with Avogadro's number, 0.6 × 10⁻⁴ power, and divide into the molecular weight of our 238. If you want to be exact, it's 238.0495 million electron volt. We said that in the derived equation, that would give us a specific power. And the specific power in that case, if you plug in the numbers here, is 0.56 watt thermal per gram. So here it is. If you have 1 gram of plutonium-238, you are producing a power of 0.5 watt per gram. Now, suppose that you want a power of 2 watts per So what do? You just use 2 grams, and that gives us an example, a way of calculating what is the weight of an isotope the specific power, 1 over the specific power gives you the gram per watt thermal. So if you want 100 watt thermal, you simply can calculate how much mass of the isotope you need. Some isotopes are not alpha emitters, and they become the basis of a new field of science, nanotechnology, in what we call micro electromechanical devices, MEMS. Tritium would be a very good choice for these devices. It provides us with electron in its decay, and any electrons means that you have a source of current, and it's a source of current on the atomic level. So tritium is a choice material for future applications in nanotechnology. Another isotope of interest is nickel 63. Now, in that case, that nickel 63 is a pure beta emitter. It does not emit alpha particles like plutonium 238. It has a longer half-life, 100 years, and the energy per disintegration is much smaller, not 5 million electron volt per disintegration, but 0.067 million electron volts. So if we substitute in our power specific power equation, you find that you need you produce 0.02 watts thermal per gram of that isotope, which is the nickel 63. Obviously, you produce much less power per gram, so you need a much larger device. What is knowing that you have calculated that specific power, and the specific power is a property of the isotope. It's just watts per gram. It doesn't tell us anything about how it decreases as a function of time. It's just, it's going to be there as long and keep its value as long as the isotope is emitting radiation. What decreases, and that's very important, is the total power emitted, because the number of of nuclei or atoms of the isotope decreases, but its specific power does not decrease. The power per unit mass does not decrease. It's a property of the isotope. So how many grams do you need to produce a certain amount of power? It's very simple. You take the number of watts that you need, divide into the specific power, watt and watt cancel out, and you end up with grams. So here it is. The design equation for the whole process is that you calculate the specific power, then you write down what is the power that you need. So let us say that you need 100 watts of power, thermal power. The specific power of the plutonium 238, say, is 0.5 watts per gram. You divide into 0.5, and you discover that simply, even without any calculation by plain logic, you need 200 grams of plutonium 239 to produce 100 watt thermal of power. This is basically the design feature that NASA follows for the production in most of its probes, depending on the electrical power that your instrumentations needs for communications, for propulsion, for the scientific measurements. This is the design equation, except that there are other design considerations that we have to go through. The isotope must be inexpensive. It should not, it is more expensive than, I would say, gold, for instance, but not too expensive to be feasible to use it. And some isotopes like plutonium 238 emit gamma radiation. So you have to shield it if you are using it in a situation where personnel is around. Some gamma radiation is associated with some beta or negative electrons and alpha emissions. Other design considerations: the fuel capsule must be rugged enough to withstand impact against rocket high velocity in the case of a rocket launch failure. It also must withstand a possible fire in the case of launch failure. Many rockets upon launch has failed, and of course they end up in a big fire. So you have to protect the environment against the release of the plutonium metal, and plutonium is an extremely chemically and radioactively toxic element in general. It must yet melt easily if the generator re-enters the Earth's atmosphere. A capsule designed for the containment of the isotope is shown as I've shown you. The whole thing for 1 watt of power weighs only 40 grams, and he's 2.5 centimeters in length. So we considered here two interesting isotopes. The one that has a half-life of long half-life, but would need a large amount to produce significant amounts of power, nickel 63, and we considered plutonium 238. I suggested that there are many other isotopes. There are thousands of them, 1,300 isotopes that we can identify in nature, man-made and in nature. 1,300. Imagine the number of isotopes we have, but they have different half-lives. So if we want to think with an engineer from an engineering perspective, you have to set limits on the choice of these different isotopes. You don't want to have basically an experiment or a probe that has a very, very long half-life. You cannot use uranium-238. It doesn't decay much, has a billion years, 0.7 billion year in a half-life. So practically, we would like to have an isotope for engineering applications that has a half-life between 100 days and 100 years. And in that case, 1,300 radioactive isotopes that humans have produced and exist in nature reduces the choices to 100 isotopes that have a half-life between 100 days and 100 years. Another design consideration is that you don't want an isotope that doesn't produce much power. Uranium-238, uranium-235 would not work in that case. So you need an isotope that has a specific power that's larger than 0.1 watts per gram, meaning that a gram of the material would produce at least 0.1 watt thermal of power. That reduces those 100 isotopes to 30 isotopes of interest. Even though others are used, the attention of the engineering community and scientific community concentrated on 8 isotopes, and I show you from those 30 isotope a list of 15 of them. It doesn't exclude the others, but this is where some isotopes are of interest to us. The most interesting one that is not unfortunately widely used is tritium. That's an isotope of hydrogen. It has a half-life of 12.3 years. A here stands for annum. Annum in Latin means years. And it has a specific power of 0.26 watt thermal per gram. That's half of the isotope of plutonium-238. But the 238 produces gamma photons, but tritium produces no gamma photons, so it's easy to deal with. In fact, as I said, it activates the phosphors in all our existing LCD liquid crystal displays on computers and phones and so on. And that those beta particles are electrons, and electrons, if you put it in a microcircuit in nanotechnology, is now a way of producing those micro electromechanical devices. So somebody can think about maybe some device that goes into the arteries of a patient and clears it up of depositions of fat or cholesterol. And so the applications in nanotechnologies are boundless. Silicon-232 is another isotope that also emits no gammas. So it's easier to use in the laboratory environment. Phosphorus-32, but the half-lives differ. This is 280 annums or years. Phosphorus-32 has a short half-life. So medical applications where you use the isotope for a short period of time and then it becomes a stable element, in that case makes it a useful choice, as well as phosphorus-33. These are beta emitters. They emit electrons, but no gamma rays. Sulfur-35, 87 days half-life. Scandium 46 is a pure beta emitter. It emits electrons, but it also emits gamma radiation. In the next chapter on food irradiation, you'll find that Cobalt 60 is a beta emitter. It emits beta particles, but it also emits gamma photon. A half-life of 5.27 years has made it a good candidate for in nuclear medicine to treat soft tissue tumors, killing the tumor with its beta radiation, as well as in the preservation of food supplies, in addition to cesium-137 in that case. Nickel 63 emits no gammas. Krypton 85 emits gammas. The Russians in their space program, in contrast to the United States, which emphasized plutonium-239, they chose a beta emitter that also emits no gammas like tritium, and that is strontium-90. It's a fission product. Strontium has properties that mimic calcium because they are in the same column in the periodic table of the elements, and it is a product of fission. So it emits no gammas, and they built many of their devices that use radioactive isotopes using that strontium-90. It has a half-life of 29 years, very suitable half-life. However, they forgot that the strontium-90 decays into another isotope, yttrium-90. And so this is a parent-daughter in the terminology of radioactive isotopes. The strontium-90 is a parent, the yttrium-90 is a daughter, so they start coexisting together as the source using strontium-90 is being used, and yttrium starts building up. But the yttrium-90 itself, now is a gamma emitter. So in the Russian space program at the time of the old Soviet Union, they built quite a few of these sources for space applications of using strontium-90 to produce electricity from isotopes. But over time, the buildup of yttrium-90 starts producing gamma radiation, and it caused some environmental problem. Is that they used that that source of electricity in very locations in Siberia, say, for a kind of for radio emitters, and in remote locations primarily, and underground. So these are called buoys for aviation. Again, buoys, B-U-O-Y-S. And over time, the radiation started being emitted as gamma radiation, and hunters in those regions of Siberia found their source of heat. So they would sit next to them to get advantage of the heat generation. And what they didn't know is that they're being subjected to very strong emissions of gamma radiation. So we should really avoid that strontium-90 unless it's used for a very short period of time, and be wary of the emissions of gamma rays from the daughter element yttrium-90. Cesium-137 has emits beta particles as well as gamma particles like the Cobalt 60. So this is a fission product, and you'll see in the next chapter that it is a good candidate for using gamma radiation, both for medical applications as well as for the food preservation process. So gammas here can kill any bacteria, any fungi, and preserve our food supply. We are losing 1/3 of our food supply to fungi and bacteria and the beetles, and food preservation by radiation uses cesium-137 and Cobalt 60. Gold 198 can be also used. We started a project building a nanotechnology little with the Draper lab at MIT to produce basically small batteries that would be 1 centimeter cube in size. But I pointed out to the group that the gold Well, even though it's a very easy isotope to use, gold is available to us, but it is a producer of gamma. So the suggestion was to use the isotope thallium-204. We used it in a factor in a design producing a 1 centimeter cube little battery by collecting the electrons from an emitter, thallium-204. It is a beta emitter and produces no gammas. It can produce batteries that are short-lived, 3.77 years half-life. And the fascinating thing about that thallium-204 battery is that after the battery produces, say, for 2 years, electricity for 2 years, no gamma emissions, you can put it back in a nuclear reactor and recharge it again by absorbing a neutron into the product isotope. You can recharge it. It becomes a rechargeable battery. We have the isotopes of 210 bismuth. Now, in that case, it emits betas and alpha particles. And we mentioned back plutonium-238. It emits an alpha particle. It emits also gamma particles. So the people working on it have to be shielded against radiation. And in addition, it undergoes spontaneous fission. And its half-life is 87 years, like in the design calculation that I have shown. Americium-241 has a much, much longer half-life. It's also an alpha, gamma, and spontaneous fission as sources of radiation. All right. Now, if you have isotopes that are emitting gamma radiation and you are designing one of them for applications in outer space in the future, based on the moon or based on the Mars, who knows what you will be doing. And you'll find that sometimes the isotopes are not used as pure metal. You use oxides. So plutonium-238 oxide is used, the cesium-137 chloride is used. And if you need really very high temperatures, strontium titanate, this is titanium oxide, that's called titanate. This is a pure beta emitter. This is a pure beta emitter here. Cobalt-60 is a gamma emitter. You'll find that depending on the temperature at which you are using the isotope, strontium titanate, for instance, can reach very, very high temperature, 1300 degrees Fahrenheit melting point in general. Because of the different emissions of gamma radiation from those isotopes, you find that you need different thickness of lead shielding, 0.1 for plutonium-238 inches of lead to shield against the gamma radiation for the personnel that are working on it. There are commercial forms for those isotopes. Let me mention, for instance, again, strontium titanate, because it can take very high temperatures. And in that case, the strontium titanate would be 55% in the metal itself. Cobalt-60 is used as a metal, as well as ruthenium-128. Polonium-210 has been used early on in the program. This is metallic. Plutonium-238 is used either as a metal or as the plutonium oxide. In that case, 80% of the metal in the metallic element is plutonium-238. So strontium-90 then, if used for a short time and accounting for the yttrium daughter, can be used as pure beta emitters. Now, we said that these isotopes emit beta particles and emit alpha particles and produce gamma rays. Gamma rays have a very long range in materials. You need maybe a meter of concrete to stop some of the gamma rays energy. So you need heavy elements, like in the chapter on gamma rays interaction with matter. We noticed that you need elements that have lots of electrons to induce the or encourage the pair production, the Compton scattering, and the photoelectric effect that would shield against gamma rays. However, beta particles and alpha particles have a short range, and they can produce heat. And then in that case, if we do not just need heat to keep the electronics above the freezing temperature in space or on the surface of Mars or on the on the moon, our two main objective for a future base on either the moon or Mars in our lifetime, we prefer to get sometimes electricity for the electronic instrumentation. So in that case, what we do is use the thermoelectricity or the thermoelectric conversion to turn that heat into electricity. And the operation of a thermoelectric generator is very simple. All you need is use what's called the Seebeck effect that you may have performed as an experiment in your physics lab. You need a hot surface on the side of an NP kind two junctions. So this would be the hot side. That will be where the isotope is. You build up a cylinder shape of an NP solid state material and a P junction of solid state material. And you notice that if you cool the other side, in that case, you find that you get a current in the external circuit, except that we are using those devices in space, and space has no air. It's a vacuum. Even the surface of Mars, the atmosphere of Mars is very, very thin. If you go on the moon, there is no atmosphere at all. So in that case, to create that cold junction, you have to use the process of radiation. Radiation would release the heat and create the cold junction. And once you have a hot junction and a cold junction between that kind of solid state device, you find yourself getting a current in the outside circuit. And the efficiency is quite high. Depending on the temperature difference, you can have an efficiency of 70% in our equation for the design. This is what that NP junction would look like. That would be the hot shoe, and that would be the cold shoe, using radiation to cool out the radioactive isotope, and you get a current. In that case, that you either store in a battery or use it directly in your instrumentation. And here is, in fact, one of those RTGs or radioisotope thermoelectrical generator. You could see the fins here, like used on water-cooled motorcycle engines and earlier propellers for airplanes that had propellers cylinders. So you could see that here the radiators is really the way that we create that cold or cool junction using the Seebeck effect. The Seebeck effect is described by the Seebeck coefficient S. It's square divided into the electrical resistivity of the thermoelectric material, divided into the thermal conductivity of the thermoelectric material, is what we call the figure of merit for the thermoelectric generator. So Z is the square of the Seebeck coefficient for the material. Again, in the lab, you would conduct the experiment with two materials, two junctions, one maybe in a beaker with boiling water and another one with ice in it. And you'll find that you get electricity moving between the two materials in general. All right, so this is a way then to produce electricity. And in fact, it is used, that process is used. As I told you, it was used in the Apollo program missions to the moon, but right now it is being used, in fact, on the surface of Mars with the probes that are operating on Mars. And this is a picture of a replica of what's called the multi-mission radioisotope generator, multi-mission RTG unit from NASA. That is a unit being used on Mars right now. Notice here the fins to radiate the heat and create the cold junction. The radioactive isotopes would be right there in the center, so that provides a hot junction, and the radiator provides the cold junction radiating temperature into the cold of space. And in that case, you get electricity in the outer circuit. This is a more detail. You could see this is 8 GPH 1, 2, 3, 4, 5, 6, 8 modules of the radioactive isotopes. And you get thermal insulation on the top and the bottom. And here, so this would be the liner. You have to protect those components, and then you have the radiator radiating into space. So that provides power, enough power for many experiments. They call it the general purpose heat source module designed by NASA. This would be the radioactive isotopes right here, but electricity now is available for running the space probes on Mars. Other than using thermoelectricity, there is another process by which we can turn or convert the heat generated by the radioactive isotopes into electricity, and that is not the same as thermoelectricity. This is thermionic. So in that case, we produce ions rather than electrons. An example is shown right here, in that you could also produce heat from a radioactive isotope on a surface of a material, and then you get another material on the top, and between them you put in a material that can be ionized. Ionized in that case means that you strip the electrons out of the atoms of the material. One choice material is cesium. So if you have cesium here and you heat the cesium, you ionize it, you have now a mixture of a plasma, in fact, of the ions that have been stripped of the electrons, and the electrons now start moving in an outside surface. And this is called a thermionic generator, whereas the one where we use the the Seebeck effect is called a thermoelectric process. So don't confuse the two. This is a picture of a cylindrical type of thermionic generator. You would have a cooled collector here, and the hot, the cesium pool comes from the bottom here. The isotope heats the cesium, and the vapor is formed, and the electrons now can be moved in an outside surface, and you get electrons out of heat. All right, third process. So what if you need not just watts level of power, a few watts of power, but you need kilowatts or thousands of watts? In that case, interestingly enough, a device designated as SNAP2 has been used. It uses a very simple, high-speed, almost turbine, but it is not a steam turbine. It is a mercury turbine. So you could see here mercury jet. The mercury in that case is heated by the radioactive isotope, and then the mercury goes and rotates the turbine. The turbine generates your electricity in an electric motor or generator. In that case, you can reach the 3 kilowatt of power. So this would be 2 feet in size, and you could see mercury in that case would be the element that is used as a working medium. Another way of producing electricity is the what's called the beta cell or the nuclear battery. And this is what we used in our thallium-204 device, as I described earlier. It has its origin in what's called the Mosley Generator. And this is a process called beta voltaic. So all you do there is get a material that is emitting electrons. So radioactive isotope like tritium or like thallium-208 or maybe even strontium-90 are emitting electrons. So you have the device here, maybe the size of 1 centimeter cube for nanotechnology applications. The electrons are emitted. You collect the electrons from an emitter on a collector, and just put your electron into an external circuit. There is a problem there that you would encounter, is that the electrons usually are emitted at an energy in the kilo electron volt. And what do you use kilovolt levels of? Maybe providing stealth for the B-2 bomber, because in that case, if you generate electrons on the surface, you create a sheath that would not allow the radar to penetrate and detect your plane. That's kilovolt of power. So you need to reduce the energy of those electrons. How do you reduce the energy of the electrons? By multiplying them. So you take an electron of an energy of 1 kilo electron volt, and you turn it into 1,000 electrons of 1 electron volt each, or you reduce the level to the 19 volts, and the electron volts. In that case, you have batteries similar to a battery of a car. So there's lots of technology to be put into it. You'll find that we also talk about optoelectric batteries using technetium-99M, and you can use electrochemical, the piezoelectric generator. Piezoelectricity is generated when you apply pressure to certain elements in general. All right, you have, there is also what's called the alkali metal thermal to electric converter. This is a technology that is really very well advanced and used to produce the power for the NASA probe. So let's look here at some of the space probes and their electrical power supplies. What we are talking about is not pie in the sky. This is the Cassini spacecraft. This is the side of a bus. It was sent into the space shuttle to the, I think Cassini was sent to Saturn. And let us look here at the bottom here. 1, 2, 3, 4. Read here, radioisotope, thermoelectric generators. Oh, there are 3 of them. 1, 2, 3. And I've shown you a picture already of one of those thermoelectric generators. So the power to all this instrumentation here, radio plasma wave subsystem and so on, antennas, radar, antenna to communication with the earth here, all of these are provided electricity by those radioisotope generators. They're not using photovoltaics because they are at missions so far away from the sun, say in the atmosphere of Saturn or Jupiter. And in that case, the solar energy flux is very low. If you use photovoltaics, you would use something the size maybe of a tennis court or even larger of a football field. So thermoelectric generator come to the help here. Notice because plutonium-238 used by NASA produces also gamma radiation, it would influence the solid state content of the instrumentation. So they're usually placed away from the bulk of where the instrumentation on the spaceship is used. Again, here this is a cutout of the general purpose heat source radioisotope thermoelectric generator. So that would be the heat source here, plutonium-238. And you notice again the characteristic fins that are rejecting heat to the vacuum of space. Radiation works in a vacuum to dissipate heat. On Earth, we have the air, so it is not radiation anymore, but convection that is used to dissipate heat when you use fins, say on the water-cooled motorcycle engines. Even in the atmosphere of the sun itself, like you say, oh, we are having a probe go to the sun, studying the magnetic field of the sun. Okay, fun, wonderful. Let's use photovoltaics. We're close to the sun. Not so. The solar radiation from the sun would destroy your instrumentation very quickly because the radiation as protons and electrons from the solar wind would destroy your photoelectric cells. So you could see here, this is the Ulysses solar probe, and it is using an RTG here. Do you see the RTG? Radioisotope thermoelectric generator. And here is another picture that gives you an idea about the size of the thermoelectric generator. Look at the hand of an engineer who is basically putting it together. As I suggested, these have been used extensively in space probes. That's another one here. That's a Galileo spacecraft. And you notice here that they have arms, one arm here. And if you read very carefully here, that's radioisotope thermoelectric generators, RTGs, 2 of them. So one should be shown here, is here. And another one shown here, again, on arms that are away from the rest of the instrumentation because of the gamma emissions from the radioactive isotopes. So the Russians, when they used the strontium-90, they didn't have to deal with the problem of keeping them away from the rest of the instrumentation. But then over time, they'll end up getting that daughter gamma rays from the yttrium-90 isotopes. Early on in all the space probes, again, these radioactive generators have been used. This is one of the early probes to Mars. And in that case, you could see it used photovoltaics here. So these are solar cells, but it's also used radioisotopes, not electric generator in that case, but RHUs, which are radioisotopes heating units. So during the day on Mars, the solar collector here, the photovoltaics, generate electricity, they store it in batteries, but tonight on Mars is below 0 temperatures. So in that case, the radioactive isotope plutonium-238 was used to heat up the electronics to keep them from freezing. Over time, they discovered that those photovoltaics lose their power generation ability because Mars is a very, very windy planet, and the atmosphere is very dusty. They get dust storms all the time. They even detected some dust devils on the surface of Mars. So if that photovoltaic generator is covered with dust, it loses its effectiveness after a certain amount of time. So later on, the trend has been to substitute for those solar cells the pure plutonium-238 electrical generators. This is a Mars rover from part of the Mars Surveyor program. And in that case, because it has a solar collectors here, it required isotopes, radioisotopes heating units. The Mars Spirit, that's named Spirit device here, that has photovoltaics also. It required the RHU units, heat generation units, to keep the electronics warm in the night of Mars. The latest situation on Mars right now is a probe called the Mars Scientific Laboratory, MSL. This is a replica of it, and there is no photovoltaics used right now. It needs lots of a large amount of power, so it's purely a radioactive isotope being used. This is named Curiosity Rover, and it is not pie in the sky. This is the way that they lowered it to the surface of Mars. It's used rockets here to bring the rover to the Curiosity on the surface of Mars. It has a whole set of instrumentations to check the composition of rocks. The idea here is to try to exploring for the possible existence of life on Mars, and people think maybe it exists in the permafrost on Mars itself. So it uses quite a bit of instrumentation that needs lots of power from our plutonium-238 sources in general. It landed in November 26, 2011 on Mars, and it is still operating right now. Some of the instruments you could see here, they give them names, but absence is the photovoltaics. It's now all using the radioisotope electrical generator. So some of the scientific instrumentation is the Mars Science Laboratory Entry Descent instrument. They call it the MEDLI, the Mars Descent Imager, MARDI, the CAM laser instrument. They like to get acronyms for, but all this instrumentation there is functional in the exploration of Mars. The chemistry and mineralogy, the rover environmental monitoring, REMS, alpha particle X-ray spectrometer. You could notice that all these instruments need electricity to function, and the cameras need, and all the information is being sent to Earth. The latest rover is the Mars Perseverance rover that is operational, and there is programs to even send more probes towards Mars in 2028, and the existing probe right there is taking samples from rocks, placing them in cylinders, and the European Space Agency is planning a mission to bring back those samples that are stored in cylinders in 2032. Oh boy, some of you may take part in those programs and have great fun. This is another picture of that latest rover on Mars, and that's named now. Every one of them gets a fine name, Curiosity. Now the latest one is Perseverance, and notice that there is no solar collector, so it's a pure plutonium-238 process in general. And this is an actual picture while that probe was being lowered to the surface of Mars. And one of the latest developments on the surface of Mars is using a counter-rotating rotor blades and helicopter that has been sent to Mars, and that would be the first kind of plane, you could call it, that is sent to another part of our solar system. You could see because the atmosphere on Mars is very, very rarefied. There isn't much air on Mars, and it's even carbon dioxide. So they have a great rate of rotations, those counter rotating blades, and then they tested it already. It can fly on pre-programmed missions on the surface of Mars. So that is creating a new capability for the exploration. It's a twin blade helicopter. Its weight is only 2 kilograms. And this is going on, and Discovery basically, eventually humans will set foot on Mars, carrying the cocktail of microbes that live on and inside our bodies with them. So we are going to turn Mars into something similar to the Earth. This is an interesting picture of Mars that shows us that the North Pole and the South Pole have, in fact, water available there in the form of ice, but it also could be carbon dioxide that is ice, very low temperatures, a very thin atmosphere around Mars. So for humans to sometimes maybe live on Mars, you would need to terraform it, maybe evaporate some of that carbon dioxide ice and water ice, and create a greenhouse effect on Mars and make it maybe livable for humans in case the Earth is subjected to some calamity, maybe an asteroid impact or a meteor impact, like what wiped out the dinosaurs 64 million years ago. So humanity, in its quest to spread life in space, may need to have a backup, or like we get backups on hard disks for all our information, a backup of life on the moon first, maybe, and then Mars, or just directly into Mars. So in that case, the radioactive isotopes would become our source of power for the remaining future in general. All right, so that is for the chapter on using radioactive isotope for power production in space exploration. I'll go to the chat room, accept questions before I start on the next chapter. Any questions? If no questions, we are supposed to have 2 lectures each time we meet, because it's the summer sessions are 2 hours in length. You have the chance to ask questions. If no questions, please do the reading of the material and then go on your own and have fun exploring the sites of Mars for whatever new information they have from. They are very public about and transparent about what they're doing and sharing it with everybody. All right, so in that case, no questions. I'll go for another application that we use for radioactive isotopes. Here I backtrack to the chapter from space applications to the chapter on radioisotope applications. In that case, another use of radioactive isotopes in food preservation by radiation. According to the United States Center for Disease Control and Prevention, the CDC, you find that 48 million cases of the, let me make sure that I am, oh boy, I am sharing here. I am sharing.
No, Professor.
It is not shared. I have to share it. Okay, here it is. Shared now. According to the CDC, in the United States, we get every year, is interesting statistics, about 48 million cases of foodborne illness. And 128,000 people get hospitalized. It is not really mentioned in the statistics. And 3,000 people die every year. It's not just COVID-19 that's afflicting us, but foodborne disease. It's much, much worse in other non-industrialized countries. The food preservation by refrigeration and drying and storage in the United States is top-notch, as well as the Europeans. But in third world countries, foodborne disease is really a disaster. Lately, for instance, in Afghanistan, they got an earthquake and foodborne disease, cholera, is spreading there. So flooding is also associated with foodborne disease, much worse than in the United States. Those among those 48 million people, it could be in any one of us right now, including myself, being subject every year to some form of foodborne disease. We end up calling it a stomach flu, and we recover, we are fine. But people with compromised immune systems, like the elderly or people who are being treated for cancer, for instance, are more prone to basically become one of those 3,000 people that you unfortunately lose every year. So the preservation of food is very important in all societies. The agricultural engineers tell me that we end up losing 30% of our food supply every year to the damage by fungi and bacteria, as well as insects, like simply beetles. And if you go around and drive around Champaign-Urbana, you find that the grain supplies are stored in those very large silos, and you not only have attacks by insects, you have even attacks by rodents, rats and mice. So all that stored food supply, wheat, soybeans, and corn, has to be fumigated using chemicals that are extremely toxic, as I'll try to show you before the end of the lectures. The irradiation of the food supplies with radiation is common in some countries like Canada and the European community. It is not as common in the United States, but its prospects are huge. For instance, instead of using ice to store fish caught in the oceans, radiation could be used, but it is not at this time. And that could substitute for many toxic substances that are introduced unnecessarily into our food supply. Imagine that you eat bread that has been fumigated to combat fungi and beetles or insects eating the grain, but it is injected into the human food supply. Patients in general, yourself or myself, when we get those stomach flus, we could get abdominal cramps, it could be vomiting, nausea, diarrhea, severe headaches, and fever. And that can cause other secondary effects like kidney failure. And foodborne disease costs us in the United States $77 billion a year in medical treatment. Some people get very sick, end up in hospital beds. There is also lost productivity. If you don't go to work, society loses your productivity, and reduced sales of products that are implicated in the food contamination probes. 1 in 6 Americans get sick from food every year. So imagine that we are maybe 30 people here. 5 of us will get some kind of food disease every year. The figures are lower than those in a 1999 report here that suggested that Americans got sick food each year, and not 33,000, but that 5,000 died in general. You hear in the news sometimes in the papers that some different foods, that fruits and vegetables are recalled because they've been contaminated with foodborne bacteria, waterborne disease or bacterial disease in general, particularly if you eat sprouted materials, sprouted seeds or sprouted beans, or even some foods that are more common, like peanut butter can have a large level of aflatoxin, and that's a very nasty chemical agent that can cause very bad diseases in general. Read more about the process of food safety in the United States here. It can save your life, and advise your friends and family. One very interesting aspect that you should be all aware of is that in 2006, a new mutation happened in a very common bacterium, the Escherichia coli O157H7. It has had a mutation that exists right now in eggs. So it is recommended that when you cook your eggs, you cook them not upside yellow side up, but you cook them on both sides. And it's not recommended that you eat eggnog at Christmas time, because they use raw eggs in its manufacture. The E. coli, Escherichia coli, is common in our intestines and humans, but they're also in the intestines of chicken. So the eggs come out contaminated. In cows, when they slaughter them, they spill out the contents of their stomachs, and all the meat gets contaminated. So in that case, cooking food and having it very well cooked is an important aspect. The E. coli O157:H7 mutation made 200 people sick in 2006 in 26 states. Salmonella in tomatoes even took a toll on 183 people in 21 states. So you have to be careful eating from those restaurant kind of salad bars. If they're not careful, they can get you very sick. Even shredded lettuce, they sell you in the stores right now. I keep objecting to my spouse buying shredded lettuce. It's easy to use to eat a salad, but you don't know how that lettuce has been washed in maybe contaminated waters. If you go to Taco Bell restaurant chain, they use that shredded lettuce. It made 152 people sick. Salmonella turned up in peanut butter, as I suggested, and it caused a nationwide recall. This is just examples of what happened in our food supply. Even though it's the best in the world, some of the food supply is in fact treated with radiation. And if it's treated by radiation, you find that it has a Radura sign. It's called the Radura symbol or sign. If I find this in a food store, this is a food I would buy, because the radiation does not affect the content of the food. It doesn't make it radioactive whatsoever, but that would be the safest from the perspective of contamination with bacteria and fungi, and even its shelf life would be longer. All right, so let us look in a quantitative way about foodborne disease and how we can make our food supply much better than, well, it already is fine, but what is recommended is the adoption on a larger scale all over the world. Some of the bacterial pathogens are listed here. This is the E. coli O157H7, but the E. coli non-O157H7, this is the mutation, and the Listeria monocytogenes. Salmonella is a very common one, and Campylobacter costas In 2000, that numbers did not change really, billions of dollars. You have to be careful when you eat chicken meat in particular, because it can be contaminated not with the coronavirus or the avian virus, but it can be contaminated with the Salmonella, Campylobacter, and all those nasty bacteria that we have listed here. Let's look at some more detail for each one of them. The Escherichia coli infections, abbreviated as E. coli, that's Escherichia coli, can cause cramps, fever, body diarrhea, kidney failure, blindness even, paralysis, and can cause death. It can be very serious. This is pictures, really, electron scanning electron micrograph of those Escherichia coli. It is not pie in the sky, it's real. It's there in the food. How to protect ourselves? Well, cooking it, and the new technology which is now proposed, which is the food irradiation in general. It can happen in flour. So if it happens in flour, then the E. coli infection, then of course your bread, the bread that you eat. And in 2016, many people in the United States were made sick by a strain of bacteria named Shigella toxin-producing E. coli, another version, 0127, that was linked to flour. And flour ends up, of course, in pastries. It ends up in bread. And there are other versions of it, ST131. So we are at risk, really. That's what I'm trying to show you here. Other than the E. coli, we have the Salmonella. You read about this every once in a while. Here is a picture of the Salmonella from the CDC, the Center for Disease Control. That the infection by Salmonella becomes primarily in shredded lettuce, in peanuts. They can grow in the peanuts that we all like to eat with peanuts and jelly in general. Another bacterium is Listeria. And so that's more serious, that can kill people very seriously. In 2011, we had an outbreak. You don't hear about them because the COVID-19 has taken over. And in fact, this is a real issue in our food supply. So let's see here. Let's learn a little bit about all of these so that we can protect ourselves, our families, and our friends. The Campylobacter happens in undercooked poultry. So if you cook poultry, please cook it thoroughly. You can get sick for 2 to 10 days, and it takes 2 to 5 days incubation. You won't feel sick until 2 to 5 days. The E. coli 157 colon H7, that happens in uncooked beef, raw produce, and particularly in spinach. Why does it happen in spinach? Because some farmers down south producing the spinach use human remains or human feces, in fact, human sewage. That happens also in Mexico for cantaloupes being exported to the United States, or they use sewage that comes out from pig farms. And in that case, the spinach gets contaminated. So if you don't, washing it is not enough. You really have to cook it thoroughly, or maybe use radiation, as I'm going to suggest here. In that case, the E. coli can get you sick for 4 to 7 days, incubation 1 to 3 days. Listeria comes from deli meat. You're not recommended to eat deli meat, hot dogs that are not well cooked, obviously, and dairy that sometimes some people think would be more healthy because it is unpasteurized. This is stupid. Salmonella happens in undercooked eggs or poultry and in peanut butter. And that's why it's recommended that when never to eat undercooked eggs, and do not use sunny up eggs, cook them on both sides. I'm giving here some cooking advice, but it's a very serious matter. Shigella in raw produce, egg salad. Staphylococcus aureus happens in meat, potato, and egg salad. Yersinia enterocolitica, that's undercooked pork, and you can get sick here for 1 to 3 weeks. All right, so again, is there a remedy for this? And the remedy that is being proposed is a new technology of irradiating our food supply that is prone to bacterial and fungi infection with radiation. Two sources of radiation are available to us. X-rays from electron beams. It's very easy for us to generate electron beams. We use them to generate X-rays. Those electron beams, when they hit a heavy element target like tungsten, generate X-rays, and you can generate different levels of energy in the X-rays. So electron beams irradiation is a method used to irradiate the materials, the food supplies that we can, where we can destroy fungi and the bacteria, and obviously to any kind of insects infestation in general. We have irradiation facilities that use the linear accelerators, that would be electron beams, but we can also use radioactive isotopes, the same as the space program uses plutonium-238. The two main isotopes that you can see in the table that I've shown you last time is cesium-137 and cobalt-60. Cobalt-60 emits very powerful gamma radiation, and cesium-137 emits gamma radiation. If you don't have sources of radioactive isotopes, as I suggested, electron beams can generate also X-rays that can kill 99.9% of the pathogens in meat. Yet it is not being used. Chemical methods are still being used for irradiating meat and protecting the food supply. The cesium-137 and cobalt-60 irradiation is not used widely yet in the food supply, but it will, I think, in the future. But it is used today in the irradiation and sterilization of medical supplies. And in fact, it is a very common procedure. You don't know that it is being that it is occurring, but in the developed countries, the medical supplies are all now being sterilized by radiation. And this is a design of a typical gamma irradiation facility. So what do? You would have a well here filled with water underground. And in that well, you place radioisotopes of cesium-137 that comes from the fission products when we are recycling fuel from nuclear power plants, or from cobalt-60. To produce cobalt-60, you get cobalt-59, a single isotope in nature. You irradiate it in a nuclear reactor, you produce cobalt-60. Cobalt-60 is a powerful gamma emitter. Now, this is underwater. Water is a good shield against radiation. So now you bring in the products packaged in boxes. That is the loading process. You send it on some kind of a conveyor belt into a maze of very thick shielding out of concrete, and you circulate it in the maze, and then it comes at a point here where you raise out of the water or tank storage pool the cobalt-60 and cesium-137 and irradiate the boxes of whatever supplies you are irradiating. So they get subjected to very powerful radiation from gamma or X-rays, and they keep running on the conveyor belt, and then they're discharged on the other side, and they are taken for consumption. Now, radiation does not affect products in the same way as heat. The energy release is lower, it's not infrared, so materials like plastic do not get deformed by radiation. So you find that in the medical field now, syringes, gauzes, plastic tubing is all being irradiated in developing nations. Still in the third world, they use syringes for injecting medications that are boiled in water, and they use steel syringes with glass, and they feel that the boiling water is going to disinfect those syringes. unfortunately, it doesn't happen in a thorough way. So we end up with HIV spreading in third world countries. We find hepatitis C spreading in third world countries too by the misuse of medical products. Some of you sometimes volunteer. We had some students from our class volunteer to help people in Puerto Rico, and they got their earthquake. And the advice at that time is for them to go to the McKinley Hospital and ask for a kit of disposable syringes. These are syringes made out of plastic. They're used only once and then thrown away in case they're subjected to any disease. The recommendations is not to use those syringes that are boiled in water and end up with very debilitating diseases, HIV and hepatitis C. So that's an advice if you travel to a third world country at any time. McKinley Hospital will give you a kit to use in an emergency. It has no implications whatsoever for drug use or any of these other applications or uses. This is just as a protection in case you get sick and you need to be given an injection of some medication. There are very good doctors there, but the materials that they use are still like, they don't have the resources basically for irradiated products. This is shows us really the tank that contains the irradiation products. So the cobalt 60 plates would be underwater. You have lights here. You can stand on top here yourself. The water provides very good shielding against radiation, but that those plates of cesium-137, cobalt 60 are raised to irradiate the food supply coming in. All right, so here is an actual picture of those plates underwater. That's a cobalt 60 source. Underwater, you'll find it glowing with a beautiful color, blue color, and that is what's called Serinco Radiation. Serinco Radiation is emitted by electrons that are moving in the water at emitting X-rays that are moving at the faster than the speed of light in water. The speed of light of water is not the same as in air, but they move at fast and they move and emit that radiation. So these are the plates underwater. And you heard about astronauts and the military generating what they call meals ready to eat. So that is really food that has been irradiated from a cobalt 60 source. So even cans of food that soldiers use in the field and astronauts use in space. You don't want astronauts in space to get a case of stomach cramping or a case of diarrhea. That would be disastrous. But the United States Army Natick Labs food irradiator picture is shown here. All those meals ready to eat are irradiated with food supply in general. Okay, we are going to take that chapter and to an advantage in which we are going to define another process by which we measure the effects of radiation. In the previous chapter, we said that radiation emits, the emission of different particles in radiation is described by the what we call the activity. So this is a unit that we use to measure the radiation in general. We define two units in that case. We define the becquerel, or 1 disintegration per second, or 1 transformation per second. And we define the Curie, which is 3.7 10 to the 10th power becquerel. And we also suggested that this is the same as the activity of 1 gram of the radium-226 isotope, the Curie in that case. Well, here we are interested in how much energy we are delivering to the food supply that is enough to sterilize it or to pasteurize it or to kill the bacteria that can cause harm to humans or to animals, in fact. So in that case, if an atom or a nucleus is irradiated with gamma rays, we have seen this in one of the previous chapters on the gamma rays interaction with matter, The electronic structure can be modified, and in that case, you can kill the bacteria because you are affecting the genes in their chromosomes in the nuclei or in their nuclei. And in that case, we measure that amount of energy that's delivered to the material by what we call the absorbed dose. The dose, of course, comes from the field of pharmacology. The amount of medication that you take is measured by the dose. The absorbed dose is the amount of energy that is absorbed by the material from ionizing radiation, not from any radiation. Like light does not have enough energy to ionize the air. Ionizing means that you strip an electron from the atom of nitrogen or oxygen, say maybe in the air. So you are left with a positive atom, that's an ion, and an electron is released. So that is ionization. Radiation that has enough energy in the kilo electron volts, like X-rays, or the million electron volts, like gamma rays, can be significant and affecting biological matter in general. So in that case, if you have these irradiation facilities, whether it is for medical products, which is routine, or for food supplies, like we are trying to advocate that they should be used, is measured by a unit in the SI system of units that we call the Gray. Mr. Gray was one of the pioneers in the use of radiation, and to honor him, it is used for the unit in which 1 joule of energy is delivered per kilogram of the material that is irradiated. Well, the purpose here is to kill bacteria, fungi, or beetles or insects in the material. So that is basically, you can call it a specific energy. 1 Gray is a specific energy of 1 joule per kilogram. 1 Gray is abbreviated as GY, and it's a small unit, so we use normally the kilo Gray. Kilo is a Greek prefix for 1,000, so 1 kilo Gray is 1,000 Gray. Well, this is an energy absorbed in a material, and it's enough to kill bacteria or kill fungi or basically kill insects in general, as we'll see in a moment. The CGS units, centimeter grams second units, preceded our use of the SI system of units, but the units are still being used today. So as engineers and scientists, we need to know both units and know the relationship between the two. In the conventional system of units, the unit of energy is not joule, it's ergs. And the unit for mass is not the kilogram, but the gram. When you consider the energy absorption of 100 ergs per gram from radiation into the food supply or the medical product, we call that a radiation absorbed dose. RAD is the abbreviation. We call that unit the rad. If you make the conversion between the joule, 1 joule is 10 to the 7 or 10 million ergs, you'll find that 1 Gray unit is 100 rads, and that 1 centigray or 1/100th of a Gray is equal to 1 rad. And so I like us, if we want to use both units at the same time and not getting confused, that we would try to remember that 1 rad is 1 centigray. Now, depending on how much energy you deposit in different materials like vegetables or fruits, avocados, onions, celery, bell pepper, broccoli, they are sold in retail stores and would have the Radura sign. And they have basically been irradiated in the case of irradiation of energies below the 1 kilo Gray or less than 1,000 grays of radiation. And if these products here are irradiated by that level of radiation, you'll find that their shelf life can be extended by up to 2 weeks. So in that case, food stores have to basically throw away all that stuff. That's a loss of 30% of our food supply to fungi and bacteria in general. So radiation preservation of food can help us reduce the amount of food that is lost, and well, it can be best fed to hungry people in the rest of the world. All right, so you can achieve food preservation by two processes. One is called pasteurizations, named after Louis Pasteur, the French scientist who is has attributed to him the process of pasteurization. And pasteurization is achieved by having low doses of radiation of 2 to 5 kilogray or 1,000 grays. And it's used only for prolonging the shelf life or storage time. If you irradiate food with that low dose, bacterial growth and fungal growth is depressed. You can increase the shelf life without those vegetables or fruits spoiling, maybe in the range of 2 to 3 weeks. If you use much larger doses, not 2 to 5 kilogray, but 10 times as much, from 20 to 45 kilogray, you'll find that you can have long time storage of the food supply without refrigeration. So what do you do in that case? You include the material, even meat or fish, into some evacuated plastic bag. You evacuate the air out of it, obviously, and then you irradiate it. That food and meat, even meat, can be, because it's sterilized, you have killed almost all the bacteria in it. You can store it without refrigeration. I repeat again, without refrigeration for long periods of time. So for instance, this is the different radiation doses for different food supplies. Potatoes and onions, if you give it a dose of 0.04 to 0.1 kilogray, you inhibit the sprouting. And all of us have stored onions, maybe in your garage or under your sink, or potatoes, and at some point you'll find them starting to sprout. When they sprout, they generate an acid called Prussian acid, and that acid is toxic. So do not eat onions that are sprouted, do not eat potatoes that are sprouted, because they become toxic and you can get very, very sick. If you irradiate them, you can inhibit the sprouting. And in fact, in Canada, they have big trucks that are food irradiators. They go to the fields where potatoes are being harvested, and they irradiate the potatoes. And in that case, they're sent to the market without the threat of sprouting for a long period of time. For grains and cereals, of interest to us here in the Midwest, since we produce grains and stores them in those huge silos that you see by the side of the roads in villages around town, you'll find that 0.2 to 0.5 dose in kilograys can disinfect them from insects. And here we protect our food supply from insects that are feeding on our grain. Fruits, 0.5 to 3 would sterilize the larvae of lodging insects. Obviously, insects lay eggs in fruits, and with 3 kilograys, you can kill those eggs of those insects, and you preserve your fruit for a long time. Fish, 2 to 8 kilogray, because if you try to preserve the fish, you have to also kill the bacteria in their stomachs. That can extend the shelf life up to 30 days. So fishermen who use now large amounts of ice to preserve the fish before it's sent to market can use it on their ships, but it is not being done, unfortunately. For meats, beef and poultry, you need a much larger dose, because beef and poultry, when you kill those cows and you kill those chicken, you spill the contents of their stomach. And we mentioned the E. coli is there. It's even in the human guts. You need a much larger doses of radiation, but that can increase the storage at room temperature for very long time. Unfortunately, as we suggested, what is used today is toxic chemicals like meat, poultry, and the beef meat is treated with ammonia, for instance. So these are toxic substances that supposedly kill the bacteria on the surface of the meat. So if you do not cook it well, still those bacteria are not fully killed. This is an example of the preservation and increasing the shelf life. In Europe, routinely, New Zealand, I think, too, strawberries here are produced. You notice that when you buy strawberries, even if you place them in your refrigerator, very quickly, some fungi start forming on them. Basically, the strawberries are spoiled and you throw them away. You don't take a risk of eating those bacteria, those fungi. These are fungi in that case. So this is a batch that is not irradiated. That is a batch that has been irradiated. You could see that the fungi did not grow there. So in that case, we have to think about the two differences between sterilization and the process of pasteurization. Pasteurization can increase the shelf life of foods, including milk. So if you milk is normally pasteurized, sooner or later, if you store it in your refrigerator, it will spoil. But sterilization is not used for milk. Pasteurization is good enough because it is consumed in a short period of time. Sterilization is more needed for other food supplies, especially grains and meat and poultry in general. This is definitely an example here. We have to implement safety control measures. This is a decay diagram of cobalt-60. You could see it emits 2 gamma photons here. We have learned about those decay diagrams at 2.1 million electron volt of energy and 1.33 million electron volt of energy. This is the one for cesium-137. Lower gamma ray energy is 0.66 million electron volts and 0.3 million electron volt. I will let you read more about the details, but I would like to jump to the conclusion of our talk today, is that gamma radiation sterilization or X-ray sterilization does not modify the nuclear structure. So it does not turn the foods that we irradiate in a deleterious way. They don't become radioactive, simply stated. What is being done today in our food supply is you go to the trade books and you find that for grain, for instance, that is the grain supplies that are stored in our area, grain is being turned into all kinds of different foods, as you know, whether it's soybean, corn syrup, for instance, in drinks, or wheat in bread. They use following what they call fumigants. Fumigant materials or fumigant chemicals comes from fumes, and it comes from the French word fumer. Fumer means smoke. They add those chemicals, phosphine, PH3OS, methyl bromide, sulfuryl fluoride, chlorpyrifos. All of these are being added today. Methyl isocyanate oil, and when you see the word cyanate here, that means that's toxic. Cyanopyrestrin, that comes from the chrysanthemum flower. Aluminum phosphide, all of these materials are used to control the growth of fungi, bacteria, and insects in our grain supplies. And it goes without saying that substituting it in our future with food irradiation would give us the same benefit that we are getting already from the medical products of irradiation of the medical, the single use of medical products, not reusing them on individuals. And that could be hundreds of thousands of lives basically saved. As the process becomes more accepted, especially in the medical field, food preservation through radiation contribution to food safety will eventually reach the same recognition as the sterilization products, as in terms of preventing the spread of infectious disease. And we are already suffering from infectious disease, the COVID-19, and we should not ignore our food supply. And I thank you for your attention. I'll stop sharing. I'll be available the rest of the afternoon if necessary, if you have any questions in the chat room. And thank you for your attention. Again, the first midterm have been set for July 1st. I'll tell you later on about how we are going to proceed with the process.